All right, in this video, we're going to go over encryption. Explicitly, we're doing AES block encryption. And I'm kind of excited for this because for a long time now, I've been like thinking about trying to do encryption for very large messages, and I've just never really gotten into it. And then the other day when I was going through a bunch of crates, I found an example that was pretty straightforward in how to go about doing it. So yeah, here's me sharing that information. Let's get it. All right. So in the aim of being thorough, let's start this video off with some definitions. I went to Wikipedia. Here's encryption. In cryptography, encryption is the process of encoding information. This process converts the original representation of the information, known as plain text, in an alternative form known as ciphertext. In layman's terms, what that means is you have your message that you would like to encrypt. We call this plain text. And then through the encryption process, you encode it into something that's known as ciphertext, which should be unreadable. Another thing I mentioned in the intro is something called block ciphers. So in cryptography, a block cipher is a deterministic algorithm operating on fixed length groups of bits called blocks. Now, if you think about that sentence just as it is and know what we know about encryption, block ciphers take the message that you're trying to encrypt and they section out into chunks or blocks, and they encrypt those blocks. All right, so the next sentence is, it uses an unvarying transformation. That is, it uses a symmetric key. So we haven't really talked about this, but a symmetric key, at least what I recall, is the idea that you have a key that you use for your encryption process, right? And that same key is going to be used for the decryption process. So now that we got that out of the way, let's go to the Rust portion. Scroll up to the top of this. So this repo is called Rust Crypto Block Ciphers. And I can't recall exactly how I stumbled across it, but if you go through the repo, you'll realize that there are a bunch of different encryption algorithms here with a bunch of different crates. And every one of these crates points to this repo. So there are many ways to stumble across this. So let's read about the crate real quick. Rust Crypto Block Ciphers. Collection of block ciphers and block modes written in pure Rust. And they have a disclaimer. Currently, only the AES crate provides constant time implementation. If you do not really know what you're doing, it's generally recommended not to use other cipher implementations in this repository. Additionally, crates in this repository have not yet received any formal cryptographic and security reviews. So from a high level, what they're stating here is that use at your own risk, which they put in bold right here. And for constant time implementation, AES is what you want to be using. Lucky for us, the example that they have in here is an AES example. So if you scroll down to the usage section, the usage section has two examples. And I'll go over the text in a moment, but the examples are right here. There's this longer one, and then there's this shorter one. And they do the exact same thing. And because of how short and concise this is, I believe using AES encryption is very approachable. So let's scroll up to the top and figure out what all of this is. Block cipher crates provide only bare block cipher implementation. For most applications, you will need to use some block cipher mode of operation, which are generically implemented in the block modes crate. So they're stating that the block ciphers are just the bare ciphers, and if you want to actually use them, you're going to have to use a block mode, which they have a crate for. Understood. This paragraph we can more or less skip over. It's talking about streaming ciphers, which I believe are a subset of block ciphers or block modes, and they have their own repo. It's stream cipher. And then we have this example, which is AES example, which is nice. 128, CBC, which is the block mode, and then PKCS7 padding. Okay. That was a lot of acronyms, and I think it's best if we just try to define those before going over the rest of the example. So what is AES? AES is short for Advanced Encryption Standard, also known in its original name as, and I do not know how to pronounce it, so I'm just not going to. But more or less, if my memory serves correctly, at one point in time in our history, there was a competition to come up with the next encryption standard. And a bunch of people submitted proposals for it. One of the proposals was this one, and this one ended up coming on top. So then it became the official Advanced Encryption Standard. AES is a subset of the, don't know how to say this, block ciphers developed by two people, this person and this person. And then coming to the 128, right? It says here that each of these ciphers have a block size of 128 bits, but 3 different key lengths: 128, 192, and 256. So the 128 that's in the name, I do not know if that is the block size or the key length. It's probably one or the other, though. Coming back here, next thing to go over is CBC, which is one of the block modes. So first we should probably look up what block mode is, and then I can show you what CBC is. Okay, so in Wikipedia, block modes come to this page: block cipher mode of operation. In cryptography, a block cipher mode of operation is an algorithm that uses a block cipher to provide information security, such as confidentiality or authenticity. So a lot of that sentence we probably didn't need, but the very beginning of it is what we really need to know. A block mode is an algorithm that uses a block cipher. So a specific type of block mode, like a CBC, is probably an algorithm used for block ciphers. And to confirm that, we can just search in this page, actually. So control find CBC. I said CDC earlier. My bad. So CBC stands for cipher block chaining. And in here they go over some of the history and then explain the algorithm a bit. So coming back to the example, next thing to go over is PKCS7. So this repo comes with a link, but this link is to the padding explicitly. Before we get there, I would like to go over what PKCS means. So again, Wikipedia to the rescue. In cryptography, PKCS stands for Public Key Cryptography Standards. These are a group of public key cryptography standards devised and published by RSA Security LLC starting in the early 1990s. So more or less, PKCS is a term for a standard, and 7, I believe, is just the 7th standard. If you're really curious about what is in this standard, you can look up the RFC, which is the request for comments, and it describes everything. It's actually pretty easy to find, just quick search. So coming back to this page and clicking on their link, here is a description of the padding and how it's done for the most part, and seemingly probably both of these, the standard, the 5th standard and the 7th standard. Anyway, padding, for those who don't know, let me explain that for a second. So what I recall is we have a block cipher, right? And the blocks are designated to work on certain size chunks. If the information that we have doesn't fill this chunk, then we need to fill in the extra space to make sure it reaches that designated size. And in order to do that, we putting things to fluff it up, and that is the padding. Okay, so that done, we can more or less go through the example. So we have AES, which is the Advanced Encryption Standard, using 128. We have block modes, and we're importing the block mode trait and CBC, which implements the block mode trait. We have block padding, which we already know this is the standard of padding. We have hex literal hex, which they use in this example. I don't know if you really need it, but their example uses it. And it's just a macro for converting hex to a string literal or string of bytes. All right, so here we create an alias for the encryption cipher. So CBC, we pass in AES, and we pass in the padding standard. Here we have the key, which we briefly mentioned because it's symmetric encryption. So you have a key that's used to encrypt, and you use that same key to decrypt the message. IV, which we haven't gone over yet, but I will go over that in a minute. Let's finish this. We have our plain text, which right now is hello world, and it should be noted that our plain text is in bytes. So you have a B in front of it. And then we have our cipher, which we initialize the cipher here. This method, new var, seems to be outdated, or at least older. There is a new version of this, and I can show you by going to the block modes documentation, which is here. So the block modes documentation, if you look here, in their example, which I believe is the exact same example that we were looking at, but updated, uses the new from slices method. And if you wanted to find this method in terms of where it was located in the repo, one way you can go about doing it is come to here, click on CBC. We noted earlier that CBC implements the block mode trait. So click on block mode. And in the block mode trait, we see the different methods. And right here, new from slices. And this is what it takes in as an input. So a reference to a slice of U8. And the same thing can be said for IV. All right, so we're back here. We create our cipher. And in this first example, what we need to do is we need to create a buffer to house everything. So we create a buffer. We make sure there's enough space for the message and the padding. We copy the message to the buffer. So here's the plain text. Here's the length of it. And then here's the copying from slice. And then we do the encryption, where we pass in a mutable buffer and the length right here. In this example, they did a search against hexes. I'm not exactly sure what I was doing I'm not sure what I did wrong or differently when I was writing this up, but for some reason my hex didn't match their hex. If that happens to you, don't feel bad or feel as though you did something wrong. What's important is that your encrypted and decrypted message those outputs are expected, or what you expect them to be. Down here, they do the decryption process. More or less, they create the cipher again. We would use the other method, not this one, but we're still passing in the key and IV. They take the cipher text, convert it to a vec, and then they pass it into decrypt right here. And then here they just verify that the decrypted message and the plain text message are the same. So coming down to the second example, which is here. This one is much shorter. They took out the initialization of the key and IV, but more or less it is you create your cipher, and then you can use encrypt vect and then pass in the plain text to here. And then for the decrypt process, you create your cipher, and then you pass in the cipher text into decrypt vect. And in terms of the parts that were taken out, the figuring out the buffer size and all that stuff, which can be annoying, is seemingly done for you under the hood. And what they state here above, and this is important, is that with an enabled STD feature, which is enabled by default, you can use encrypt vect and decrypt vect. So you can use it this way. If you do not have this feature enabled, then you're seemingly going down this route. So I mentioned earlier that I was going to cover what IV stands for. And in order to do that appropriately or properly, we need to go back to the block modes wiki page. All right, so we're back. And the second paragraph covers it. So scrolling down, most modes require a unique binary sequence, often called an initialization vector, IV. For each encryption operation, the IV has to be non-repeating and, for some modes, random as well. The initialization vector is used to ensure distinct ciphertexts are produced even when the same plaintext is encrypted multiple times independently with the same key. So we're going to pause right there. The IV stands for initialization vector, and its importance is in the last sentence I mentioned. So if you have a message, right, and you're encrypting and decrypting it, and you have a key that you use to encrypt and decrypt this message, if you want the ciphertext that is produced when you encrypt this message to be different or distinct, then you have to use different IVs. I.e., if you use the same IV and key every time you encrypt, you will produce the same ciphertext, which makes the whole process of your cryptography that much weaker and easier to figure out. So my takeaway and the things I've looked up online is the best practice is to always use a different IV every time you do encryption, but just save it someplace, because in the decryption process, you have to use that same key IV pair. All right, so now that we've finished going over the example here, I'd like to open my terminal and then show you how it works when I ran it. All right, so this is the repo that I created. Well, not repo, just directory I created to mess around with this stuff. And in it, everything's pretty standard. I put my examples of my different cases in examples. I also have a Peter Pan book here because I messed around with encrypting and decrypting a large message, i.e. a book, Peter Pan. But before we get to that, let's first look at my cargo.toml file so you see the dependencies I use for this. So if you look here, the first three dependencies are needed for the example to work, which is AES, block modes, and hex literals. The fourth dependency is because when I was doing this in my free time, I forgot what hexes were and had to relearn and discover them. And then, so let me show you the file for the first example, and then we can run it. Source main. This file is almost identical to the one that we just read through. There are some differences, and I'll just point them out real quick. Here, line 4, I imported the hex that I used to figure out what hexes were because I was messing around with it. And line 6, I imported string because I wanted to print out the plain text. So if we noted earlier, and I can show it down here, plain text is bytes, right? But if you want to print it out, then you need to convert it back to a string, and that's what I was using the string library for. So string from UTF-8 and pass in the plain text. Everything else is more or less the same. I have the updated method, which is new from slice, new from slices. And I commented out the assert and opted to print everything out to screen. So that's it for the most part. Let's run this. Cargo run. Here's the key. Here's the key encoded. Here's IV. Here's IV encoded. Here's the plain text that I converted so I can print it out the screen. Here's the ciphertext. And here's the decrypted ciphertext. So as you can note here, the plain text and ciphertext are the same, which is what I want. A quick reference to hexes, just in case if anybody else was having trouble remembering what they were. They are a numbering system that's in base 16 that goes from 0 to 9. Then you have A, which is 10, B, C, D, E, F, and F being 15. The key, which is just a string, a series of numbers from 0 to 15, can be seen here. So this is 0, 1, 2, here's 9, here's 10, 11, 12, 13, 14, and 15. And IV, which we have 240 here, and it goes all the way up to 255, is the same way. So we have F and 0. F we know is 15. 0, this is a base 16 system. So if you think about base 10, right, it'll be 15 times 10. But this is base 16, so instead it's 15 times 16, which gives you 240. And then we just increment up from there. So F1, F2, yada, 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 all the way to FF. And yeah, that was the long example. So I also wrote out the shortcut example using the encrypted vec and decrypt vec methods. So let's look at that real quick. Vim examples, I called it shortcut. And everything here is more or less the same as the other one, with the exception of two things. I changed the IV because I wanted to demonstrate something, but let me change it back real quick. This originally was FF, as we just went over. If we scroll down, here's where it gets different. We have the encrypt vec, and we just pass in a pointer to the plain text, and we did 2vec. Cool. And then in terms of the ciphertext, it's just a pointer to the ciphertext. Everything else is the same, or it should be. And let's run this. So we can see the key is the same, key encoded is the same, IV is the same, IV encoder is the same, plain text, everything here is the same as the previous one. And we scroll up. Oh, let me scroll up this way. So one thing I want to harp on is IV. So earlier we noted that if the IV is the same, then the ciphertext is going to be the same, given that you are encrypting the same message and using the same key to do it, right? And we can see that here. So the IV is the same in both, the plain text is the same in both, and the ciphertext is also the same in both. They start with 128, and they all go to 212. So one of the claims that the Wikipedia page made is that if you change the IV, then the ciphertext will come out differently. So let's verify that. Vim. And easiest way to change this is to make the last one 0. So let's run this again. We see that the IV is now 0 at the last one instead of 255. And the ciphertext is different. So the last one started out with 128. This one is 109. But the decrypted message is still the same. And the plain text was still the same. And the key didn't change. But the ciphertext did. So that proof that changing the IV will give you a slightly different ciphertext, which is what we want. All right, then lastly, I messed around with trying to encrypt a large message, which was the Peter Pan book. And let me show you that real quick. Vim, examples, large message. So again, everything in here is more or less the same, with the exception of I'm importing file system on line 6 because I need to get the book from the file system. And I did here at line 21. We have file system, read to string, Peter Pan. And one thing to note is that when I passed it into encrypt vec, I had to do a pointer, plain text, and then use the method as bytes because we're passing bytes in. So though I know that like lowercase str string is really just a list of bytes, if you use as string, it gives you an error, and I can demonstrate that real quick. String, and I remove this real quick. And it states that it's just not the right type. So explicitly, you should be using bytes here. Bytes are king. Let me just change this back real quick. And then from that point, everything else is the same. We have the decrypted ciphertext, just pass in ciphertext there, and then we print it out the screen. So let me run this. Ta-da! It was pretty uneventful, but we just encrypted and decrypted an entire book, which means this is viable for pretty much anything I would want to do in the future. All right, with that, we've reached the end of the video. I hope this was useful, helpful. If you liked the video, hit like, subscribe, yada, yada, yada. Outside of that, peace.